All right, we're down almost to the end here. One of the last topics we want to talk about here is nuclear transmutation. Now, the roots of chemistry lie in alchemy. And one of the goals of the alchemists was to take cheap metals and turn them into more expensive ones. And they called that transmutation, turning tin into gold or lead into gold. That doesn't work. But we can do transmutation on a nuclear scale with a lot of high dollar equipment. Enough equipment that it doesn't make it worth doing this for monetary gain. So nuclear transmutation occurs when we take smaller elements and we accelerate them in a particle accelerator. So the first particle accelerators, which is kind of like the CERN Large Hadron Collider, but there were others that were made 50 years ago, 60 years ago. So it's a large underground track, like a racetrack. And it's all controlled by very, very sensitive electromagnets. And so we take some ions and we introduce it into that field and we pump their speed up. We can push them with magnets because they have a charge. By sequentially turning on and off the magnets, we can push them and accelerate them in a track that's maybe 2 miles, 3 miles in diameter, and we accelerate them fast enough that they approach the speed of light, maybe half the speed of light. We get them moving so fast that when we change their path and collide them into a target that's made out of the atoms that we're wanting to study, those ions that have been accelerated and particles hits with such velocity that their nuclei penetrate each other and they start to fuse together. And we can actually turn a smaller atom into a bigger one. By doing this, it's not just any random thing. You got to be careful. There's recipes for what you can do. But doing these sorts of called nuclear bombardments, these nuclear bombardments, we can turn something like 14/7 nitrogen. If we accelerate alpha particles going around this loop and we hit them at the right instant, at the right speed into a target of nitrogen atoms, we'll make oxygen 17. And then there's usually some leftover parts. Kind of like when you put together a dresser from IKEA, there's usually a screw or a bolt or two left over because they put some extras in. Here there's extra parts left over because we didn't need them to make the atom that was the most stable one that could be produced. These are always mass balanced just like all of our other reactions. So, for example, if I'd given you this much of it without the neutron there, you should be able to figure out what the missing particle is by mass difference and charge difference. Okay, so these equations still balance the same way. They just look a little bit differently because we're not doing a fundamental process. We're doing a laboratory imposed process. So we can take something like 27/13 Al plus alpha particles to produce phosphorus 30. In this case, there's also a leftover neutron. In both of these instances, we took the two stable isotopes. Nitrogen 14 is totally stable. Aluminum 27, totally stable. But by colliding them with a high energy nuclear particle, we're able to transmutate those stable nuclei into something else. And a lot of times the something else that we make is not stable. Oxygen 17 is going to be neutron rich, right? So it's likely to undergo a process that will make it more stable. Phosphorus 30, on the periodic table, the mass of phosphorus is about 31. So this is a neutron poor element. So it's not uncommon for us to take a stable isotope, convert it into an unstable isotope that then undergoes a nuclear decay process. And it's called induced radioactivity. We take a stable one, collide it with a particle to make an unstable one that then undergoes other processes. And there is a recipe, if you've got a particle collider sitting in your backyard just doing nothing, on page 228, or sorry, page 928. That doesn't sound right. 28 doesn't sound right. Let me find it. Yeah, some tables on 979, 978, talking about how we can take an atom and collide something with it to make something else that undergoes decay, and there's some more over there on the other side. I'll hold them up here. Kind of maybe you can see a little bit. Okay. Now, come exam time, I'm not going to ask you to come up with a recipe. You don't have to know the recipes. But if I gave you one of these equations that was missing one of the particles, you should be able to fill it in. If this was missing the alpha particle, you should be able to figure out what its mass and charge number must be and come up with an alpha particle. Just regular balancing of nuclear equations. Okay? Now, beyond transmutation, we have nuclear fission. And fission occurs when a big nucleus becomes two smaller ones. So, splitting of large unstable nuclei, I'll say a nucleus, large unstable nucleus, into two smaller ones. And remember what I said during the binding energy video. The two smaller atoms don't require total as much binding energy as the one bigger one did. So there's extra energy that's given off in this process. Okay? So breaking of a large unstable nucleus into two smaller ones that are each more stable than the original one was. Okay? Extra particles are often released. So there's usually leftovers, because the smaller the atoms get, the fewer neutrons they need. So there's usually neutrons left over on these. So one of these cases where we take a large, whether it's stable or just relatively stable or kind of stable, take a large nucleus and we initiate a nuclear decay. In this case, a fission, where we take it and fuse. Technically, alpha emission is fission because we split a helium nuclei out. Remember, alpha particles are helium nuclei. So technically, fission is also part of alpha decay. But we take a large nucleus and we split it, and the splitting doesn't have to be equal. We can make one very small atom and one just small atom. They don't have to be the same size. No, we're not creating two of the same atom. That's why there's so many different emission particles for nuclear fission processes. So we can take something like uranium-235, which is relatively stable. It has a half-life of something like 4.5 billion years. So it's radioactive, but it's not very radioactive. And if a uranium-235 atom collides very strongly with a neutron hits it square right in the middle and penetrates the nucleus, we get uranium-236. Uranium-236 is very unstable. That's going to undergo fission very, very quickly. And possible products might be 90 over 38 strontium, or strontium-90, plus 143 over 54 xenon. I'm running out of space there. Plus 3 neutrons. Okay. So 1 neutron in results in fission that creates 2 smaller atoms. So this part, that fission, releases a huge amount of energy because it takes much less energy to hold 38 protons in one spot plus 54 in another than it took to hold 92 in one spot. Releases a huge amount of energy and creates 3 neutrons. Okay, now think back to World War II and the Manhattan Project that developed the first atomic bomb. We have a reaction here that takes a relatively stable isotope, long shelf life, meaning it's not going to go off at any undetermined time when it's a weapon. We introduce a neutron to that source. We create a highly unstable isotope that immediately, within nanoseconds, undergoes fission processes and releases more neutrons than it absorbed. So if this piece of uranium-235 is big enough, a big enough piece, those neutrons all get reabsorbed. So one reaction becomes 3, and then 3 reactions become 9, and 9 become 27, and you have a chain reaction. And if it's allowed to go untethered, it will just run away with itself. And in a few nanoseconds, you have all of your uranium undergoing fission, creating all of this energy in a very tight window. And that was the impetus for developing the atomic bomb. A huge amount of energy released in a tiny spot. That's a bomb. That's the definition of a bomb. Okay? So we've made it through all of our chapters. We are done. Congratulations for making it this far. I know it hasn't been easy. I know you've had a lot of stress. I'm proud of all of you for all the work you've been doing. And I really, really miss seeing you guys sitting right there. I hope to talk to you soon. I hope you stay safe and have a great summer. Okay? Bye-bye.